Hi, my name is Julia Fleischman, and today I will be sharing my results and conclusions from Lab 1 in Intro to Physics at Georgia Tech. In this report, I will introduce and explain the purpose of this lab, share my results from my observational model as well as my computational model, and then compare the two. Once we cover the results, I will then conclude my findings and extend my knowledge by answering conceptual questions. The purpose of today's lab is to observe an object's constant velocity. In my experiment, the object is a regular tennis ball. We can see that the system is a tennis ball and the surroundings include everything around it like the floor and the force that I use to roll the ball. We'll observe the tennis ball's constant velocity by designing and simulating an experiment through a software, model the experiment with code, and then compare the graphs of time versus position between the experimental model and the computational model. Before we start discussing my results, there are key concepts that you should know prior to doing so. Newton's first law states that a resting object will remain at rest unless it is acted upon by a force, and an object in motion will remain in motion unless it is acted upon by a force. Newton's second law states that a force is equal to its mass times its acceleration. These two laws are used to be able to form these two formulas shown on the screen, the velocity update formula and the position update formula. Performing this experiment, I assumed that there was no air resistance or friction upon the tennis ball, which causes our net force to be zero. Since the net force is at zero, it allows us to state that the tennis ball is in constant motion. I took a video of a tennis ball rolling across the floor and inputted it into the tracker software. Tracker was able to record the position of the tennis ball over an amount of time. Using its features, I set the axis in which measurements are determined to be that right is positive and left is negative. After recording the ball's position over an amount of time, our observational graph resulted in this. It's important to know that in the video we used, forces such as friction and air resistance were present, and so it is not possible for the observational graph to be a strict linear graph, and rather it is slightly curved. For my computational model, mass is negligible in this instance because in the velocity update formula, since our net force is zero, mass is canceled out. I found my initial velocity vector by calculating the average velocity. I was able to determine delta t by analyzing my table of values and saw that each time frame lasted 0.033 seconds. This resulted my initial velocity to be 0.6556 repeating. I then edited the while loop by plugging in the formulas previously introduced in this video, the velocity update formula and the position update formula. I was then able to run the code and simulate the experiment with no friction or air resistance. These are the graphs that resulted from the computational model. Here, we can be assured that the program was able to calculate the position and velocity versus time accurately, as the slope in the position graph is constant, and the slope in the velocity graph is zero over the whole time frame. When we compare both the graphs of my experiment and the computational model, it becomes much more clear that the observational model had problems in simulating an environment with zero net force. The red line is my observational line, and it reveals that the tennis ball was decreasing in speed and velocity over time, but in the computational model, the ball remained in constant motion. This is due to just outside forces such as friction or air resistance acting upon the ball, in which it causes it to decrease in speed. Now we move on to further understanding. If we oriented the axes, the result would be the same, but instead of a positive slope, the graph would reveal a negative slope. We would still observe that the computational model is better able to simulate an environment with zero net force. We also cannot determine how many pushes and pulls are added together in this experiment to result in zero net force because in real life, many forces are present in the tennis ball's surroundings, and we failed to account for those during the experiment. To achieve a more accurate result next time, we should recognize that there are more forces acting on the ball other than gravity itself. To conclude, an object is capable of being in motion despite there being no force present. This is due to Isaac Newton's second law, which states that Isaac Newton's first law, which states that An object in motion will remain in motion unless a force is acted upon it. In real life, however, it is difficult for an object to remain in constant motion due to additional forces such as friction or air resistance consistently being present in our environment. Thank you so much for taking the time to watch this lab report, and I hope you have a great rest of your day.